So I'm Anjum. I'm a threat researcher at Endgame. At Endgame, we build an awesome hunt platform, and I work on network security aspects of it. Like a lot of research in InfoSec, I really owe a lot of work to some of these guys, especially Joe, who is an in-house exploit kit expert, and also the author of Maxwell. Chris and Sean to give this project a lot of DevOps love. And finally, Brad and Caffeine from Malware Traffic and at Caffeine for working tirelessly to track malwares and giving us the data to work with. So last year, I was working on domain reputation, domain scoring and stuff, and exploit kits were becoming a big challenge. None of the traditional ways or features of classifying domains would work for exploit kits. So I started digging deeper, and it came down to this multi-stage attack chain that exploit kits use. So malware that spreads using exploit kit have three different stages: redirect, exploit, and infect. And what's interesting is that these stages are managed by, it's not managed by a single entity. There are three different components at play that are very loosely coupled. So if you look at any report from Malware Traffic or Caffeine, you'll see something like sudo dark leech, redirecting to neutrino, dropping Locky. And so these are three different components, three different players that are working together to make this happen. On a network level, it looks like this. So a user visits the website. It may already be compromised, or it may have a malicious ad that redirects this user to a series of gates. Now, gates are like bouncers. They filter out unwanted traffic to exploit kits. And they are intentionally hosted on throwaway domains like dynamic DNS, URL shorteners, and stuff like that. And so they get replaced very often. Once you get past the gates, you end up on an exploit kit landing page. Again, the exploit kit landing page is rotated really often from exploit kit. Quite often, a same user may not see the same landing page ever again. And so once you're on the landing page, the browser gets exploited, the binary is dropped, and again, the binary might change over time. So what I'm trying to highlight here in this slide is that there's a lot of dynamism at play. There are a lot of moving parts. Domains and content gets swapped in and out really frequently. So given this challenge, I started looking at what tools and techniques we have at hand to look at exploit kits. And they broadly fall into two categories. One is to detonate a URL in a sandbox and then observe the artifacts from the OS. Now that's a really thorough approach, definitely, but the challenge is the cost of VM management, starting up a VM, saving the state, coming back to it. So you really can't scale that really well. On the other end of the spectrum, we have tools like JS Detox, we have Revelo, we have a lot of JavaScript engines that let you walk through the code, deobfuscating on the run by applying breakpoints at specific DOM manipulation functions. So that's another good approach to understand what happens in the browser, but you have to manually debug the code to understand what's going on. So that gave me an idea that there's a gap between the two approaches, and maybe we can find a midway. Could we find a way to understand what happens in a browser when an exploit kit executes, and without having to manually go through the code? So enter headless browsers. Many of you might already know about headless browsers. These are frameworks that let you interact with the browser without having to load up the GUI. Phantom.js is the oldest and the most widely used one. It's usually used for QA automation and stuff like UI testing and stuff like that. And it's built on top of WebKit. Slimmer.js is another one which is built on top of Firefox, which has the same Phantom.js API. So these frameworks have some interesting API that let us do what we want to do. They let us inject a JavaScript into a page before the page is loaded. So that gave me an idea. Instead of doing breakpoints, could we hook onto the JavaScript functions? Could we just apply the hooks to all the functions that say Revelo lets you breakpoint into and intercept the calls? In addition to that, these frameworks have tools like a lot of event handlers that let you intercept HTTP requests and so on, can abort a request, modify the request and so forth. And finally, you can change the user agent and okay. change the user agent to look like IE and stuff like that. So that was the first idea, and I thought, all right, so I'm gonna do some JavaScript hooking on all the functions that Revelo lets you hook onto. So document.write and eval and all the stuff like that. And when I say JavaScript hooking, it looks like that. Let me warn you guys, I'm not a JavaScript programmer, so this may look ugly, but it works. So it's basically replacing the original function with a wrapper that logs the request, the responses, and optionally calls the original function and responds back to the caller. That's the skeleton of it. So armed with this code, I loaded up a particular exploit kit, and this is, I think, sudo dark leech going to neutrino. So the first phase, redirect. There's not much code here. A regular website may have a small iframe that gets injected somewhere, or a small JavaScript that runs and injects an iframe, but basically not much obfuscation. Really, 2 lines, 3 lines of code that's hidden somewhere. So that's easy to get past. Then we enter the series of gates. Like I mentioned earlier, gates are meant to filter out traffic that the exploit kit doesn't want to target. Think about it, there's an infrastructure that you don't want to expose to any random person, any random HTTP request. So there are gates in place to make sure it just redirects that unwanted traffic out of exploit kit's path. The way the gates do this is, firstly, they use client-side checks. There is going to be browser fingerprinting, OS fingerprinting. It's going to look for AVs. It's going to look for sandbox environment. It looks for headless browsers in some cases. In addition to server-side, client-side checks, it has some server-side checks. There are exploit kits that are known to target specific countries. There are exploit kits that exclude a certain set of countries that they know they have risk of getting persecuted. I would imagine a lot of IP ranges are excluded. So you find that if you try to reach out to these websites from AWS, you won't get the real data. So there's a lot of server-side checks in place as well. And this is where you start seeing a lot of code obfuscation and encryption. Let's take an example. So this is again the sudo dark leech code. As you can see, there's this whole span element which is hidden and has some code that looks really different from the rest of the code. And then there's this JavaScript that's highly obfuscated. I don't think you can look at a JavaScript and find out what's going on. But one thing I can highlight here is that it defines a lot of variables and assigns character values to it. Towards the end, it starts appending these variables in a particular manner to make up a string of code and basically evals it. After 2 rounds of deobfuscation, I remember, code starts to look like this. It's doing browser fingerprinting. As you would imagine, it's going to look for the user agent and look for IE sort of substrings in there. But what I want to highlight here is the first line where it initializes a variable using window.sidebar and window.chrome objects. Now, window.sidebar is only available in Firefox, and window.chrome is only in Chrome. So if any of these objects are not undefined, the value is not 0. And subsequently, the code fails to decrypt. Once we get past the browser fingerprinting, we get to the decryption phase. And this is how the code looks like. The first line has the key. Second line, you can see it's pulling the code from the span element. The decryption routine is a very typical sort of string manipulation where you have alternate calls to string.from char code and char code add. And finally, once you get the decrypted string, it's passed on to a function constructor. Function constructor in Java, function prototype in Java is basically a function constructor that takes a string argument and returns a function that evals that code. So that's how the code executes. And that code, again, looks like very similar to this sort of redirect to the exploit kit landing page. Let's look at one more example. This is Rig VIP version that came out after Rig. It's a newer exploit kit. This exploit kit does something more. It looks for specific browser idiosyncrasies and assigns probability of a browser being Firefox or Chrome or IE, and then towards the end it calculates whether it's really IE or is it a bot, and based on that it makes a decision on whether to redirect to the exploit kit or not. So our first take have some drawbacks. It wouldn't work, right? So what have we learned? Firstly, we need to replicate IE's window object. We want to look like IE. So literally I enumerated all the properties in IE's window object and replicated that in Firefox. The next slide has some code on how to do that. Secondly, our function hooking we should be hooking onto more functions, literally go wild on these. It may make the output more noisier, but you'll catch more stuff. So hooking function prototypes, DOM manipulation, string manipulation, event handlers, just added a lot of more function hookings to a lot of these functions, literally just, like we saw the code earlier. And lastly, we saw the use of window.navigator object. That's another sort of sub-object that I've seen being used heavily to detect browsers. So Navigator has OS, Navigator has plugin MIME types that are used often to see what sort of browser it's running. Speaking of modifying an object to look like something else, this is how attribute hooking looks like. So you can define getter object, a function on an object, on a particular attribute, and that function gets called anytime that attribute is accessed. So this gives you another hook into attribute access. You can choose to return a different value, you choose to hide it, do whatever you want with those particular attributes. So once we have this particular code in place, the original code run through this JavaScript looks like that. There's a lot of data there. I actually removed arguments and resolution to make it fit in a single slide. But think about this. In a single second of execution, that sort of calls, you get that sort of call stack that you can make sense of. You understand what's happening here. So that's the first win. Some exploit kits go a step further. They use plugins and ActiveX plugins to look for AVs. This particular code example is from Magnitude, I think, and it's looking for Kaspersky ActiveX objects. Similarly, there is another vulnerability in XML DOM. Well, there was a vulnerability in XML DOM for IE8 and below, where you could load an XML with a path res : and look for file paths based on how based on the error, you can find out whether a particular file path exists or not. And this was used heavily to look for drivers, to look for sandbox environment, to look for AV's artifacts. So with such objects, we need to sort of introspect a little harder. That's where proxy objects come into picture. Proxy objects, basically, as the name suggests, are man-in-the-middle proxy to a particular object. You can define handlers that are called anytime a particular operation is performed on an object. If you're a Python programmer, this is like descriptors. So here's a simple example of a generic ActiveX object. You can define get and apply function to look for attribute access and function calls. But you can take this idea further specifically for XML DOM object and implement exact interface of an ActiveX object. So for XML DOM, I implemented load XML attribute and returned a function proxy for that particular attribute access, and I was able to capture all the file names that exploit kit was looking for. So that gives us the ability, so for good measure, imitate a human behavior. You could regularly insert some, move the mouse, insert keyboard events, and keyboard events, and look like there's a human element there. So with all that code, and again, this is like, I would say 500 lines of hacky code, you have a call stack of whatever happens in a browser. You have the attribute accesses over this call stack. We get to see what plugins and what ActiveX the browser is looking for. If we have defined any particular ActiveX plugin to the proper interface, we see exact interaction with the plugin. We get access to cookies, we get access to DOM, so we can extract iframes, objects, extract the artifacts of the exploit and for out-of-band scanning. And finally, we get access to navigation requests that we can man in the middle and modify on the way. So what can we do with this output? At the least, we can write signatures, and these are all over the place. The signatures here are from Maxwell that we use in this project, and literally you can search the text for these signatures and find existing exploit kits. But this framework lets you take this idea a little further. You can write signatures on arguments to documented write, arguments to function prototype. So post decryption data is available to be written signatures on. I haven't tried this, but I really want to try writing signatures, figuring out what decryption keys are used and reuse of decryption keys across exploit kits. But signatures are brittle. It's an arms race. We write a signature, author will change the code. So we could do better than that. So here are some of the features that we started collecting on the data to be able to classify whether a website is definitely bad or something suspicious is going on. And if it looks suspicious, maybe we should run it through a sandbox. So invisible off-the-screen text box with weird entropy that we saw earlier is a telltale sign of encrypted code. Alternate calls to string manipulation functions like these are used heavily for decryption. Function constructors seems quite fishy. ActiveX objects looking for AV, definitely bad. XML DOM looking for file paths like XML DOM, loading XML that starts with res : double slash, definitely bad. And lastly, you could look at JavaScript code and be able to find out whether this is obfuscated, minified, or plain simple JavaScript. I did a simple diagram analysis and it was able to classify really well. But if you have your machine learning chops, a convolutional neural network would do this really, really well. So what do we have here? So this is a new approach that you can use to build a fast, low interaction honeypot that at the least does everything that a JavaScript deobfuscators let you do. Understand what's happening on a browser while an exploit kit is executing. You can spoof your way through gates. You can extract the exploit artifacts, Flash files and Adobe exploits for out-of-band scanning from VirusTotal and such. And you can, at scale, look for signatures for known exploit kits. And that's it. Any questions?
I've got a question. Are you going to make these slides available? Sure. I mean, if you want to tell them, because there was a lot of code in there. I don't know.
Okay, on peer list?
Yeah, maybe so, yeah.
It's called
Peer list, LI, yeah.
All right, so I haven't yet put the slides on the peer list, but I will put it up there for in discussions because there's a lot of code over there, so I'll put it up there.
So I bet you know what I'm going to say next. On behalf of BSides and Fitbit, we'd like to thank Anjum